everybody, and welcome to my fourth and final physics video. This video is focusing on the physics of an instrument that I love, the piano. So let's get started. As you can see in this picture, there are 88 keys in a piano, and each key has a different frequency. Each key has a different sound wave that's associated with it. Starting with A0, the frequency is 27.5 hertz, all the way up to C8 on the furthest right of the keyboard, which is at 4,186 hertz. Now, what a lot of people don't realize about our near and dear piano is that it's actually a string instrument. As you saw in the introductory video, and as you'll soon see again, I have a baby grand piano, and as you open up the back of the piano, you can actually see the strings and see the hammers hitting the strings, which initiates the vibrations that produce the fundamental frequencies we hear that most of the time create really pretty noise, but whenever you're banging on the piano and hitting random keys, it's not always pretty, but I like to think that it's always pretty. So moving on, you can see this is a diagram of the pedals in the piano. The pedals are at the bottom of the piano. There's three of them: the soft pedal, the sostenuto pedal, and the damper pedal. And whenever you press them, there's different sounds that result on the piano. So the leftmost pedal is the soft pedal, or una corda. It shifts the keyboard beneath the strings. It brings it down a little bit so that the hammers can't strike as many strings, giving it a softer sound. The center pedal is the sostenuto, or sustain pedal, and that disengages the dampers, so it allows the sound to stay, and you don't have to hold down the key for the sound to continue. And then the right pedal is the damper pedal, which also sustains, but it also dampens the entire keyboard. You'll be able to see a lot of movement in the back of the piano each time I hit the pedal that corresponds to the hammers moving up and down to create the desired effect. So once again, I'm going to play Muzio Clementi's Sonatina, Opus 36, number 3, Spiritoso, once with each pedal. Enjoy. So you saw at the end of those two videos that I held my hands up and kind of wiggled them in the air. That was just kind of to emphasize that I was not holding down those notes. That was all the pedals doing the sustaining. And that's just something really cool about the piano, that you don't constantly have to put in that work to hear the note. So now to emphasize the fact that a piano has strings, we're going to look at the strings in my piano. I'm going to play a chromatic scale, which is all the way from A0 at the very left of the keyboard to C8 at the far right. So as you could see in the last video, all the strings aren't the same size. So the first 10 notes, first 10 keys have one string apiece, and those are the really low notes. They have thicker strings. The next 18 pitches have 2 strings apiece, and the last 60 have 3 strings apiece. Now these strings get decreasingly thin, and they all have different lengths, masses, and tensions. The tensions are maintained so that there are 12 equal semitones per octave. And an octave is the same note, but it appears higher or lower. So the common example is middle C. So if I were to sing 2 octaves of middle C, it would be da, da. And so now I'm going to play middle C on the piano. I'm going to play it chromatically so you can compare me plucking the chromatic strings all next to each other to what you just saw in the video of me playing the chromatic scale on all the piano keys.
Go.
Now, the piano is not tuned evenly. Actually, at the low end and the high end of the piano are tuned so they depart slightly from equal temperament because it's more pleasing. It's been judged to be more pleasing to the ear whenever they aren't completely in tune with each other, and that has to do with the tension. Now, the frequencies that you hear whenever the string is plucked, whenever it's hit, that's the fundamental frequencies that we so often learn about in our physics classes. The fundamental frequency equation, which is F equals the velocity of the wave on the string over 2 times the length, describes to us how an octave works and why those notes sound the same. So if you start at, for example, middle C, which I sung before, and go up to the next higher C, the tension increases by 4 factors, and the frequency increases by 2 factors. And we indeed see that the frequency does double in the calculation. So next I'm going to play a little tune by Mozart that I think you'll all recognize. First I'm going to pluck it on the strings, and then I'll play it on the piano, so I hope you enjoy. So thanks for watching my video. I hope you learned something new. I hope maybe you start to play piano, and I hope you have a wonderful day, as always.